We have already seen two methods of finding integrating factors. Integrating factors are those functions using which we can reduce a non-exact differential equation to an exact differential equation. Now in this presentation we are going to see three more rules of finding integrating factors. Rule 3 is applicable to those differential equations where m and n are homogeneous functions of same degree. Rule 4 is applicable if the differential equation is of this pattern, where it is y into some function of xy is our n and x into some function of xy is our n. Rule 5, here the integrating factor is of the form x raised to h, y raised to k, where h and k we are going to find using the condition of exactness. Some conditions are there on n and n for which the rule 5 is applicable to that differential equation, but we will see those conditions later on after solving one problem using this rule. So we begin our presentation with rule 3. In rule 3, if the differential equation is m dx plus n dy equal to 0, where m and n both are homogeneous functions of same degree, and xn plus yn is not equal to 0. Here xn means all the terms in n are multiplied by x plus all the terms in n multiplied by y. Normally in many books it is written as mx plus ny. But since we use the notation for partial derivative dabba m by dabba y is m subscript y and n subscript x. So to avoid the confusion between m into x and m subscript x, I am writing it as x into m plus y into m. If this is not equal to 0, then reciprocal of that is 1 upon xm plus yn is an integrating factor of the given equation. Let us see one example. Consider this as a differential equation. Now here, each term of n has a degree 3, xy square, total degree is 3, y cube degree is 3. Similarly, all the terms in n, they have also degree 3. So m and n are homogeneous functions of degree 3. So let us calculate xn plus yn. So xn means 3x square y square minus xy cube plus xy cube, because we are going to multiply this complete term with y, minus 2x square y square. Then this minus xy cube will get cancelled with this xy cube and the remaining term is x square y square. So my integrating factor is 1 upon x square y square. So now multiply the complete equation by 1 upon x square plus y square and we get it is 3 upon x minus y upon x square into dx plus 1 upon x minus 2 upon y dy equal to 0. Since it is an integrating factor, this must be exact, but always check whether it is exact or not. So what is dabba by dabba y of this term? It is minus 1 upon x square, and dabba by dabba x of this is also minus 1 upon x square. So equation 2 is exact. Now you know how to solve exact differential equations. So its solution is this. If you don't remember how to solve exact differential equations, or you have not seen the videos on exact differential equations, revisit the videos on exact differential equation and try to solve this problem, which is an exact differential equation, and check whether your answer is this or not. Even though you have any difficulty or doubt, you can mail me on my mail ID also. Okay. So the method is simple. If m and n are homogeneous functions, calculate xn plus yn. If it is not 0, its reciprocal is integrating factor. Then reduce the given differential equation to exact one and then solve the exact differential equation. One important thing here is, you may remember that if m and n are homogeneous functions of same degree, we can reduce the given differential equation to variable separable form using the substitution y equal to ux. We have seen those things in our video on reducible to variable separable form, differential equations which are reducible to variable separable form. So you can solve the same equation using that method also, that substitute y equal to ux and follow the procedure. So solve this problem using that method also and decide whether which method is simpler to you, that this method or that method. Again, two things are there. Two limitations are here for this method. One is if xn plus yn is equal to 0, we can't apply this method. So in that case, we have to use this method only. And second limitation is if this xn plus yn contains more terms than 1. Here it is only one term, x square, y square. But if it is x square, y square plus something, etc. In the integrating factor, those terms, they come at the denominator because we are taking reciprocal of xn plus yn as considering integrating factor. And if there are more terms at the denominator, when we multiply our given differential equation by this integrating factor, sometimes our m and n in the new differential equation, which is exact, they are so complicated that their integration is not straightforward, or we have to use some simplification, substitution, etc. to integrate them. So in that case also this method may be simpler. So it's your choice. For homogeneous functions of same degree, you have two methods. Either find the integrating factor or using the substitution reduce it to variable separable form. So we will move to rule 4 now. If the differential equation is of this type, that is my m is y into some function of xy and n is x into some function of xy, then xm minus yn is not equal to 0, then reciprocal of xm minus yn, that is 1 upon xm minus yn, is an integrating factor of the given equation. Let me elaborate this m and n further. See, what do we mean by function of xy? Function of xy may contain algebraic terms like x square, y square, x cube, y cube, in short x raised to h, y raised to h. Such terms can be there as function of xy. Similarly, sine of xy, e raised to xy, ln of xy, these are functions of xy. Now my m is y into some function of xy, that means m contains algebraic terms like x raised to h, y raised to h plus 1 always, because it is y into function of xy. In function of xy, the term should be x raised to h, y raised to h. Therefore, in m, the algebraic terms should be x raised to h, y raised to h plus 1 always, and then y into sine of xy, y into e raised to xy, etc. Similarly, in n, the algebraic terms should be x raised to h plus 1 into y raised to h, and the terms like x into cos of xy, x into ln of xy, like that. So, if such things are there in m and n, our differential equation is of this form, and if xm minus yn is not equal to 0, this is an integrating factor. Okay, so let us consider one example. Here all the terms are algebraic terms. In m, degree of y is more by 1 than degree of x at each term, and here degree of x is more by 1 than degree of y in each term. So this differential equation is of this type. If we take y outside, then it is x square y square plus xy plus 1, which is a function of xy, and so on. So my differential equation is of this type. So let us calculate xm minus yn. So xm minus yn is x cube y cube plus x square y square plus xy minus x cube y cube minus plus x square y square minus xy. So after simplification, we get it is 2x square y square, which is not equal to 0, and therefore the integrating factor is 1 upon 2x square y square. But we know that any constant multiple of an integrating factor is again an integrating factor. So for simplicity, we will take integrating factor as 1 upon x square y square. Then multiplying by this integrating factor to our given differential equation, our new differential equation becomes y plus 1 by x plus 1 upon x square y dx plus x minus 1 by y plus 1 upon x square dy equal to 0. Let us check whether it is exact or not. So dabba by dabba y of this is 1 minus 1 upon x square y square, and which is same as dabba by dabba x of this, because derivative of x is 1 and derivative of this term with respect to x is minus 1 upon x square y square. Since these two partial derivatives are equal, our differential equation is exact. Now follow the procedure of solving exact differential equations and you will get your answer is this. So rule 4 is straightforward. If the differential equation is of this type and xm minus yn is not equal to 0, this is our integrating factor. Again, if this xm minus yn contains terms more than 1, somewhere it is difficult to integrate the m and n in new differential equation, which is exact. But it's okay. At that time we have to use either simplification or substitution, anything to solve such integrations. Now we will move to our last rule, which is rule 5. Right now I am not mentioning any condition on m and n. It is the integrating factor is of the type x raised to h y raised to k, and we are going to find h and k such that after multiplying by this term with given differential equation, our equation is exact. So we will solve one problem and then we will impose the condition on m and n. Okay, so start with this problem. Consider this differential equation. For this differential equation, let us check whether we can solve it by our previous methods or not. Okay, so first of all, this is not in variable separable form. M and n are not homogeneous. They are not function of ax plus by, so we can't reduce it to variable separable form. Further, my dabba m by dabba y is 4y plus 4x square and dabba n by dabba x is 4y plus 9x square. They are not equal, so it is not exact. Their difference is 5x square. And if we divide by this difference to m or n, we are not getting a function of x or function of y only. That means first two rules of finding integrating factors are not applicable here. Another thing is this m and n, they are not homogeneous functions, so rule 3 is also not applicable. And here degrees are not like in the rule 4, that means that condition is not satisfied here, and therefore rule 4 is also not applicable. So though it looks like very simple differential equation, any of our method which we have done so far not applicable to this differential equation. So for such a differential equation, let us check whether our x raised to h y raised to k can be integrating factor or not. So multiply the equation by x raised to h y raised to k. So multiplying it, my m becomes, m is now 2 into x raised to h y raised to k plus 2 plus 4 into x raised to h plus 2 y raised to k plus 1 plus n is 4 into x raised to h plus 1 y raised to k plus 1 plus 3 into x raised to h plus 3 y raised to k. These are my m and n. We are going to find h and k such that this differential equation is exact, means dabba m by dabba y is equal to dabba m by dabba x. So let us calculate dabba m by dabba y and dabba m by dabba x. So dabba m by dabba y is 2 into k plus 2 into x raised to h y raised to k plus 1, differentiating with respect to y, plus 4 into k plus 1 into x raised to h plus 2 y raised to k. And dabba n by dabba x is equal to 4 into h plus 1 into x raised to h y raised to k plus 1 as it is, plus 3 into h plus 3 into x raised to h plus 2 y raised to k as it is. So to find h and k, we equate these two partial derivatives with each other. Now we can see that the term here x raised to h y raised to k plus 1 is also present here, and they are equal means their coefficients must be equal, and same is true for next two terms also. So we are getting two equations in h and k. The first is 2 into k plus 2 is equal to 4 into h plus 1. Coefficient of these two terms must be equal. And second is 4 into k plus 1 is equal to 3 into h plus 3. That means 2k plus 4 is equal to 4h plus 4, and therefore 2k is equal to 4h. So k is equal to 2h. The second equation is 4k minus 3h is equal to 9 minus 4. So it is 4k minus 3h is equal to 5. If I put k is equal to 2h, it is 8h minus 3h, that is 5h is equal to 5. So h is equal to 1, and therefore k is equal to 2. So xy square is my integrating factor. Let us multiply our differential equation by xy square, and so my new m is 2xy raised to 4 plus 4x cube y cube, and m is 4x square y cube plus 3x raised to 4y square. Let us check whether dabba by dabba y of this term is equal to dabba by dabba x of this term. It is 4 into 2, 8xy cube plus 3 into 4, 12x cube y square. And the same thing here, 8xy cube plus 12x cube y square. So equation 3 is exact, and the solution is x square y raised to 4 plus x raised to 4 y cube equal to c. Now we want to determine the conditions on m and n, for which this x raised to h y raised to k can be an integrating factor. So let us recall our previous step, this step. Here I can take these two equations and h and k because the terms are same here. That means x raised to h, y raised to k plus 1, and it is also present here. And the same is true for this also. Now, this happens because here in m, if x raised to h, y raised to k plus 2 is one term here, x raised to h plus 1, y raised to k plus 1 is a term present in n, where degree of x increases by 1 and at the same time degree of y decreases by 1. Similarly, whenever x raised to h plus 2, y raised to k plus 1 is a term here, x raised to h plus 3, y raised to k is a term here. And this is because in our original m, same thing happens. If y square is here, xy is here. That means degree of y reduces by 1 and degree of x increases by 1. And for x square y, x cube is here. So if such a condition is satisfied, x raised to h, y raised to k can be an integrating factor. Because we are getting such terms, sorry, here y raised to k should be there. It is some mistake, printing mistake. So, if such terms are there, we can get two equations in terms of h and k, and so we can solve them. But again, one thing is there, even if such term is not there, that means x raised to h, y raised to k plus 1 is present here but not here, that means this coefficient should be 0. In that case, we can get more equations, more than two equations in between h and k. If all of them they are consistent, we can still calculate h and k. But that is not possible always. If they are not consistent, then this method is not applicable, or we cannot find integrating factor using this method. But if none of them is possible, that means no other method we can apply to given differential equation, always try this, whether x raised to h, y raised to k can be integrating factor or not. But we will write the condition on m and n first, and these are: my differential equation should be of the form, if some x raised to a, y raised to b term is present in my m, corresponding to that term, there should be x raised to a plus 1, y raised to b minus 1 should be there in my m. And similarly for second case also. And in that case, again, if mn minus pq is not equal to 0, then x raised to h, y raised to k is an integrating factor. So, exercise is there, 3 problems are there, but for 2 of them, there are more integrating factors than 1. In fact, for equation 1, you can find 2 integrating factors using rule 3 and rule 5 both. So, find them, solve the differential equation using them, check your answers whether they are same and with this they are same or not. Again, since the m and n are homogeneous functions, you can reduce it to variable separable form and use that method also for this differential equation. So, in fact, there are 3 methods to solve this differential equation. The second one, clearly it is a function of xy into y plus function of xy into x. So, rule 4 is applicable, but still rule 1 is also applicable. So, find the integrating factors and try to solve using both the methods, and last one is also there. If you have any doubt regarding exercise, you can mail me on my mail ID and you will get the guidance. Till now, whatever we have done, we have seen 5 methods of finding integrating factors, and using those integrating factors, we can solve the non-exact differential equation by reducing them to exact. But how can one say that if m and n are homogeneous and xn plus yn is not 0, then always 1 upon xn plus yn is an integrating factor? That means some proof should be there. And all these proofs, all the proofs of 5 rules, we are going to discuss in our next video, which is on proofs of all the rules of finding integrating factors. Till then, bye. If you like the video, share it with your friends, subscribe to the channel Jitnyas Academy so that you can get more notifications of more such videos. Thank you.